Hello everyone, my name is Wang Bowen and I'm a member of the VirtIO team at Xiaomi. Today, I'm going to talk about the NuttX VirtIO framework and its future works. I have divided my presentation into three sections. The first section is the introduction to VirtIO, which includes the VirtIO architecture, the VirtIO device spaces, and how the virtual queen transfer data. The second section is the NuttX VirtIO framework, which includes the framework architecture, the VirtIO API introduction, and how a VirtIO driver works. The next section is the future works of the NuttX virtualization, which includes the VirtIO PCI transport support, the virtual host framework, and the virtual socket support. Let's start from the first section. Firstly, I want to introduce the VirtIO architecture. VirtIO, or virtual input and output, is the interface that allows the virtual machine to use its host's devices. The red figure shows the overview of the VirtIO architecture. The VirtIO architecture has three parts. The first part is the VirtIO drivers, the blue part in the red figure. We also call the VirtIO drivers front-end drivers. They are in the Ghost OS and accept I/O requests from user and transfer them to the backend drivers. The second part is the VirtIO devices, the orange part in the red figure. We also call these devices backend drivers. They are in hypervisor and hand the I/O requests from the VirtIO drivers by uploading them to the host's physical hardware. The next part are virtual queens. Virtual queens are the communication channel between the driver and the device. They exist both in the driver and the device side, and the implementations must follow the same standard from the VirtIO spec. Next, I want to introduce the VirtIO device basis. The VirtIO device contains 5 basic parts. The first part is the states. The states indicate the driver's states in device initialization. For example, in the final stage of the driver initialization, the driver set states to driver OK to notify the device that it can start driver the device. The second part is the feature bits. VirtIO uses bit field to represent the driver and the device support features. An example is the VirtIO block device uses bit 5 to indicate whether the device is read-only or not. So the driver should read this bit fast and should not send the read request to the device if this bit is set. The third part is the configuration space. VirtIO device provides some configuration data to the driver by using this space. An example is the VirtIO block device places the total sector number in the configuration space. So the VirtIO block driver needs to read this space in the initialization to get the capacity of the VirtIO block device. The next parts are virtual queens and notifications. They are used to transfer data between device and driver, and I will describe this process in detail in the next slide. The red figure shows the data transfer process from the VirtIO driver to the VirtIO device. But before to explain it, I want to introduce the virtual queen first. As we can see in the red figure, the virtual queen contains 3 parts: the variable ring, the descriptor table, and the user ring. The virtual queen uses the descriptor table to describe the buffers, And one descriptor can describe a buffer by using an address and a length, like this. The available ring and the user ring are both the ring buffers. They store the described table index. If we get an index from the available ring or the user ring, we can get a descriptor table. We can get a descriptor in this descriptor table, and then we get this buffer. Okay, back to the data send process. The VirtIO driver wants to send the data to the VirtIO device. The first thing is to allocate a buffer from the shared memory. And then the VirtIO driver will fill the send date to the buffer and add this buffer to the described table. And next, the driver will add the corresponding described index to the available ring and send a notification to the VirtIO device. The VirtIO device will get the corresponding index from the available ring and find the buffer from the described table based on this index. After the VirtIO device consumed this buffer, it will return the buffer to the user ring and also send a notification to the VirtIO driver. The driver finally will get back the buffer and free this buffer. And now, the data send process finished. Okay, now let's move on to the second section. The second section is NuttX VirtIO framework. First, I want to introduce the VirtIO framework architecture. The right figure shows the architecture diagram. The blue parts represent the VirtIO drivers has implemented in the NuttX. These drivers follow the VirtIO spec, convert the I/O requests from the user to the VirtIO operations. And the orange part in the right figure represents the VirtIO framework. The VirtIO framework has two parts. The first part is the OpenMP. OpenMP is a library for asymmetric multiprocessing system and has provided the most VirtIO API. The second part is the two new features based on the OpenMP in NuttX. The first feature is the MMIO transport support. The MMIO transport can make the VirtIO drivers interact with the VirtIO MMIO devices. And the second feature is the VirtIO bus. The bus provides a match mechanism for the VirtIO drivers and devices, just like the Linux bus mechanism. Next, I want to introduce some commonly used VirtIO API in VirtIO drivers. The first API is the virtual queen add buffer. This is a data send API. The driver can call this API to add a buffer list to the virtual queen, and then the device can receive this buffer list. The second API is the virtual queen kick. This is a notification API, and the driver can call this function to send a notification or interrupt to the VirtIO device. And normally, we always follow a virtual queen kick after a virtual queen add buffer, so the device can handle the driver's requests as soon as possible. The last API is the virtual queen get buffer. This is a data receive API. The driver can call this API to get the buffer returned by the VirtIO device. And importantly, the return value of this function is the cookie passed in the virtual queen add buffer. Now, I want to take an example to show you how the VirtIO driver works in NuttX. I take the VirtIO block driver write operation as the example, and the right figure shows this process. In the write operation, the first thing for the driver to do is to build the write request. From the VirtIO spec, the VirtIO block request data structure has shown in the right figure. We follow the VirtIO spec and set the type be write, and the sector be start sector, and the date be the user buffer. After build the request, we call the virtual queen add buffer to add this request to the virtual queen, and then follow a virtual queen kick to notify the device to handle this request as soon as possible. And next, we will wait as before until the write operation finished. And let's move on to the VirtIO block device. The device gets the request and write the data to the real device. Then he will return the request to virtual queen and notify the driver the write operation has finished. After this, the VirtIO driver will receive an interrupt, and in the interrupt handler, the driver will call the virtual queen get buffer to get the waited semaphore and post the semaphore to wake up the write operation. And finally, the write operation finished and return. Okay, let's moving on to the next section. The next section is the future works of the NuttX virtualization. The first future work is the VirtIO PCI transport support. The NuttX only supports the MMIO transport for now, but is not enough for some cases. The right figure shows an example. If we want two NuttX running in QMO to use the API message service, for example, the API message file system or the API message socket, we need to use a VirtIO device called the IntVM shared memory device. Because this device provides the shared memory and the cross-core interrupts support, and these are the API message service needed. But unfortunately, this device only supports the PCI transport. So this is why we have to support the PCI transport. The second future work is the virtual host framework. The vhost is a backend implementation solution for the VirtIO. Just like the VirtIO framework provides the ability to implement the front-end drivers, the vhost framework provides the ability to implement the backend drivers. And as we can see in the right figure, if we have implemented the vhost framework and the backend drivers, we can make the application run in the main CPU to access the physical device in the slave CPU directly. The next future work is the virtual socket. Virtual socket is a fast and efficient communication mechanism between the ghost virtual machines and the host. The right figure is the virtual socket architecture diagram. It can be divided into three parts. The first part is the interface to the socket framework, just like the Unix domain socket and the API message socket in the NuttX. The second part is the ghost to host transport. This transport is based on the VirtIO framework and can be used to communicate with the host vSOC. The next part is the host to ghost transport. This transport is based on the vhost framework and can be used to communicate with the ghost vSOC. So we can see in the right figure, you will have implemented the ghost-to-host transport for the VSOC. We can make the NuttX application running in the kernel communicates with the Linux application by using the standard socket API with the VSOC address family. This is because the Linux kernel has implemented the host-to-ghost transport. And more, you will have implemented both the ghost-to-host transport and the host-to-ghost transport. We can make the two NuttX applications running on different CPU communicate with each other by using the VSOC. Okay, that's all my presentation, and thank you for listening.